Now, in addition to the fact that I could have capacitors in series and I could have them in parallel, I could also have some combination of those. Say here's our battery, and let's say we've got 10 volts. And we run up here and we've got two capacitors through here. Those are in series with each other. And let's say we throw another branch in the circuit that looks like this. Now that branch is in parallel with these two. Right? We still want to know how much total capacitance there is in the circuit, because total capacitance and the voltage, that's where we figure out how much total energy there is in the circuit, etc. But we can look at these, and I'm going to go with different values. Now I'm going to say this one's a 5 microfarad. I'm going to say this one's a 15 microfarad. I'm going to say this one's a 25 microfarad. Okay. In order to break this down so that I can figure out how much voltage is stepped across each place. So for instance here, this sees positive 10 volts here. This sees negative, or this sees 0 volts here. We don't know how much is dropped across each one of these. This one, it's seeing positive 10 here, it's seeing 0 here. That's got 10 volts dropped across it. But what we want to do is rewrite this circuit, the simplest that we can, by combining capacitors together. So in this particular case, I want to take these two that, as they're drawn there, are drawn as being in series, and I'm going to rewrite this circuit where I'm going to represent them in a more simple way. So I got my 10 volts down here. Still got a 25 microfarad capacitor here. But in between here, I want to know what is the value if I was to write that as a single capacitor. Now, why I want to do that? Well, if I write that as a single capacitor, then all I have to do is add those two together in order to figure out what the total capacitance is. And then I can start working out how much charge there is, sort here and there, etc., how much voltage is dropped, all those kinds of things. So I look at these two and I say, well, those are in series. Therefore, the total capacitance of those two, 1 over 5 plus 1 over 15. Again, that looks like 3 over 15 plus 1 over 15, which is 4 over 15. That's 1 over C total. Therefore, the total capacitance is 15 over 4, also known as 3.75 microfarads. That means here, I can simply write 3.75 microfarads. And then again, I want to make this as simple as I can, so I want to rewrite this and say, okay, what I really want is the simplest it can be. One voltage source, one capacitor. I rewrite this thing to reflect that. Where I say, okay, I've still got a 10 volt source, comes up here, but I'm going to pretend that those two run together. So instead of rewriting that as if they are two separate branches, I'm rewriting that together as one single branch. The thing comes back together over here. And I want to look at that and say, well, how much total capacitance is there? And I say, well, for parallel system, the total capacitance is you just add them together. 28.75 microfarads. So I say, okay, then this is 28.75 microfarads. Now I got 28.75 microfarads. I have 10 volts. How much charge do I have? Well, I can look at how much charge do I have total. So the amount of charge that I have, well, we said that the charge is a relationship between these things. Q was equal to C times delta V. And so I know the total capacitance, 28.75 microfarads. I know the total voltage, 10 volts. That tells me 287.5 microcoulombs. That's the total charge. Now, when we think back to this step, that's the total charge on the entire set of capacitors. When we think back here, we think, well, is there that much charge on each capacitor? And the answer is no. Some of it comes down here, some of it goes here. This one is a lot smaller. This one has about 7 times the capacitance this one does. So a lot more charge is going to go here than go here. How can I determine how much of those charges? Well, I know the total charge is 287.5. But what else do I know? I know that this capacitor right here sees 10 volts across it. This set of capacitors here sees 10 volts across it. So I can look at that top one. And again, working with this equation right here, I can say, well, total charge that I have on capacitor, let's say capacitor, the top capacitor, top, would be what? It would be the capacitance of the top times the voltage. And the capacitance of just the top is 25 microfarads. And the voltage is 10. Therefore, 250 microcoulombs is how much charge is on the top. Now, if there's 250 microcoulombs there and it's 287.5 total, I can either multiply 3.75 times 10, or I can simply look at this and say, well, 228.75, 287.5, I'm sorry, minus the 250 leaves me with 37.5, but there's going to be 37.5 microcoulombs down here. And then we go back one step further and we say, these two are in series. How much charge is on each one of those? But in series, the amount of charge that is induced over here, or that is over here, induces charges over here. So those are going to be equal. So each one of these has 3.75 microcoulombs. And this one still has this 250. And I can look at this and say, how much voltage is dropped between here and here? Well, the voltage drop, again, it's the same equation, just rearranged a different way. Delta V is equal to Q divided by C. And right there, between there and there, I know I have 3.75, I'm sorry, 37.5, put my decimal in the wrong place. I have 37.5 microcoulombs. I have 5 microfarads of charge. And therefore the voltage there, 37.5, that's 7.5 volts is dropped from there to there. And the total voltage is 10, so again, I can either subtract or I can do the calculation. This is going to be 2.5 volts that's dropped across the second one, because 10 minus 7.5 is 2.5. Or I can say 37.5 divided by 15, and that's also going to